what we're going to be going over here is an example where we're going to be calculating the marginal product of a production function. And our production function is really similar to the Cobb-Douglas production function. Okay, so this is the function that we're going to be dealing with here. Q is our output, and that really represents our total production, or the value produced. In our case, it's going to be looking at some revenue here, and that equals Y. And Y is our total factor of productivity, and really that's going to be revenue per unit of product that we're able to produce here. And you take that times some material and some labor here. So again, material, M here stands for the input value here for material, times our labor here, and labor stands for the input value of labor. And these are really unit amounts here, and they're raised to some exponential amounts here. And those exponents here, A and B, there's really the share of the productivity of the output that M and L here represents. Okay, so if we go down here and really we'll look at our profit here is equal to revenue minus some cost here. Okay, so going back to our production function here, Q here. Well, first off, let's look at our function here. What we're going to be really looking at is our portion here where we got some revenue on a $1,400 per unit of revenue times whatever units of material and labor that's required to produce this product here. So let's understand that. So the revenue here is on a per unit basis, and that's really represents our Y value that we mentioned above here, and that's the units parameter. So we're dealing with money here, units or revenue of $1,400. So that's what our output's going to be here in dollars here. And then M here, again, that's our units of material and our labor here. And we did a regression analysis on this problem. We determined that our exponential amounts for this production function for material, in this case, is 0.5035, and for labor is 0.3215. And really what that's saying is that that's the share of output. It's really scaled, or that's what being contributed here to the share of output. Material is giving about 50.3% of the revenue, depending on what unit you have here in material, and the same for labor. Labor represents about 32% here of the revenue per unit here, again depending on the units of labor that you have here. And then you would subtract from it the cost on a per unit basis here for both your material and labor. But we're not going to use this in our calculations here because it starts out with some negative amounts and it really doesn't add anything to our solution. Okay, so we got these two inputs here. Material and labor raised to some exponential amounts, and they equal the output here. So really what we're looking at when we're talking about marginal product here is the output of the last unit that we add here for material and labor, and that's what really we're going to look at. Now if we solve for this production function here, we would have come up with some equal product curves or iso-quant lines here, and really those are lines here where you can really substitute material for labor, but in our case we're not going to be doing any substitution. We're just looking at exact amounts here for material and labor here. But based on these iso-quant lines, because they are curved here, we can differentiate along those lines to determine the exact marginal product that we're looking at. So we'll start here looking at the first unit of product that we have here for material and labor, and we'll move up to the point here where we come up against some constraints here. So what I'm showing this green area is just our feasible solutions. We really don't have to be terribly concerned with that. And then we had a couple constraints here regarding our labor and material that we have here. But what we're going to do here is this marginal product. So this is where we're going to look at the measure of the output of the last unit added here of material and labor and get an understanding what that is. Okay, so let's go up here and continue on. Okay, again, marginal product of labor and material, it really measures the output here of the last unit that we added. So let's just look at it in these simple terms here. Let's just assume, again, we have this output here, that our production function here. And let's just say for material, we have 60 units here, and for labor, 120 units. Okay, so just going into our equation here and solving for material, raise it to the power here, 0.50, you're going to come up with 7.85 units here, or that's the value here based on 60 units of material that's being added. You take that times the $1,400 per unit here for revenue, and you're going to come up with your material here is going to be $10,990 here. So just taking and looking at it on a unit basis here to $10,990 divided by 60 units here of material, and you have 183 units here, or $183 per unit here, which material is adding to the output or to our profit that we'd be looking at in this case. So the deal is here, you take away 1 unit here of material here, and you lose $183 in output. So that's, in simple terms, that's what we're looking at here as far as our marginal product. Do the same here for labor. Just say labor, so let's say we had 120 units here of labor. That raised to 0.3215 here is equal to 4.66. Take that times $1,400 revenue per unit. So our labor is going to be $6,524 here. That goes to the output, but you divide that by 120 units of labor, and you're going to get $54 here per unit with labor's adding here on a unit basis. So this is these quantities here that I'm showing here, those would be for the total output, but just on a unit basis, in this case, it's $54 per unit here for labor. So you take away 1 unit here of labor, and again, you're going to lose $54 here in output. Okay, so basically that's what you're looking at for marginal product. But now, this is the way you want to go about it here. Your marginal product output of the last unit added, you just do a partial derivative here of that, of our function that we have here. What you do in a partial derivative, you take a derivative of one of the units here and you keep 1 unit constant. Now really, what I've done here, you might want to have a software package where you can just plug these equations in and it'll give you the derivative of the amounts. I happen to use MapleSoft here, but we'll just go through it and this is about as basic as you can get as far as a derivative. We'll just go and solve for it here, but really when you're working with these units and you've got these odd exponents and so forth, you're going to have some sort of software package. You can do it with a calculator, but it would be good to have a software package so you can solve for, get your solutions here, whatever it may be. So here was our equation that we had here. So let's take our first derivative here. Let's look at the material here, the marginal product of our material here. So what you want to do in this case, the material here, you first take that exponential amount here, 0.503, that becomes your coefficient here in your equation, and then you subtract minus 1 from it, and that's going to give you what? It's the minus 1 from 50 is 4.956, so that's really a negative amount, so that becomes your denominator here. So M, you did a partial derivative here. A happens to be that $1,400 here, and you left L constant in this case. L, whatever it is, you just left it alone. L, and its exponential amount, 3.25, you just left that constant. So this is your material here, your marginal product of output here in your material. So for each unit here, you can determine what your marginal product is when you add it in here. Okay, so that's for material, and just to go through labor, it'll be the same thing here. So in the case of labor here, you would hold your material constant. So M here raised to its exponential amount, you just leave that in here. A stays in as it is here. That's your revenue here on a per unit basis. But for the labor here, this is where you do your differentiation. You have that exponential amount, 3.215, subtract 1 from that, and that's going to give you a minus 0.6785. So that becomes your denominator here in your equation here. This is a labor, the marginal product of labor, and that 3.215 here, remember that was just taking your exponential amount that you had here, and you take that becomes your coefficient here in your equation. Okay, so that's pretty much about as basic as you can get here for a differential equation, but that's how you'd go about doing them. Okay, and then what you want to have is, of course, you'd want to have some software package where you just put these numbers in and it's going to give you the value. So if we look here at the case where we had that A here was $1,400 here, and M, I just put it in at $60 here, and L at $120, and based on our equations here, the margin product of material, 430.25 here. So based on adding 1 unit, or at 60 units here, exactly at 60 units of material, that based on our revenue here, $1,400, and our differentiation we've done here for marginal product of material, we're going to get $430.25 on a per unit basis here based on that exact $60 or 60 units of material. And same for labor here. Labor, we use 120 units here. So the margin product labor, put that in your equation here, and you're going to get 137.37. So that's what a marginal product, that's what it's adding here to your output on a unit basis based on 120, exactly 120 units. So it's really just looking at one of those units here exactly at 120 units. And it's same for material, looking at one unit here at 60 units here. So that's what you're looking at, and we'll go and we'll look at those now in looking at it, and we plotted them out here in 3D and get a little better understanding of what they are here. Okay. All right, let's look at it now in 3D to understand this marginal product here, where we're going to be looking at decreasing returns. Now, if you just looked at this equation up here for our output, our production equation here, it's really not intuitive to understand exactly what's going on when you're adding extra units of material and labor here. But if you lay it out in 3D here, you get a better understanding of what's going on. So when we're talking about a marginal product here, we're decreasing returns here. We'll start out by looking here at our first 3D here. So shown in blue here, greenish blue, that's our marginal product of material here. And we start out here with 0, and we increase it up to here 150, and along this, and that's shown here in green or bluish green here, and then in gold here, that's our marginal product here of labor here. So these are the equations that we came up with, those differential equations when we solve for the marginal product material here, and then marginal product of labor here. Okay, so you see what's going on here. So our marginal product starts out here, it actually increases, but if you look at it here in terms of material, say that when you start out with 0 units here, well, any fraction of units here, and you're not going to make fractions, but whatever, you start out with a high marginal product. You can see if you had just a fractional amount here, you'd start out with like 2,000 here in a marginal product being added here in to your output. But then as you add more and more units here in material here, you can see it's decreasing sort of exponentially based on that equation we have here, that in this case for material it was at 0.5035 here. Okay, so you can see it's decreasing here. And the same for your labor here. I'm showing that in gold again here. And you start out with 0 units. Well, you'd have like marginal product would be 2,500 here. Well, you didn't build 0 units, but that's the way the equation works. But as you increase your units here in labor, you can see the marginal product, or what's going into your output here, is decreasing. Okay, and these 2 dots here, these 2 spheres here, I actually put those in here, and they're kind of misleading here, but just to show the fact here that the marginal product here of material here is higher than the marginal product here of labor here based on that equation we have up here. So these dots here represent the same point for the marginal product's different, but for that particular output here, that is the difference that we have between material here and labor here. Okay, so this marginal product here, decreasing returns, that is, it's adding, as you increase your labor amount of units of labor and material here, you're having less going into your output here than you are what you had when you started initially here with lower units. And if we just moved over here to the output here, our output here, Q here, I'm showing that was that profit that we're looking at here. You can see what's going on here. Again, material here, we're increasing it here from 0 to 150. Labor is going from 0 to 150 in this way. And these little dots here, these spheres here, that's really our input. I just put those in here for material and labor here. And that's what, based on the equation we have, it generates this output here, or profit, essentially a profit here. And right up here was the with the constraints that we had here, this was our maximum output at 70 units of material, 78 units of labor, and it produced 48,144 here. Now to remember, that doesn't include, we didn't include the costs of material in that. We just left that, material and labor, we just left that out. We just looked at our revenue portion here of our production function here. But again, you can see what's going on here. It's when you have 0 units here, you have a high output here. But as you increase the number of units, it's little. You can just look at the curve here. As you increase your units, your output is increasing, but at a much slower rate here. And that's because that marginal product here in your equation is going down here for both your material and your labor. So you're flattening out. Your curve is flattening out here. Okay. Now we could move, maybe we better move, and remember this was our function here. Q equals that, just our function here. That was our profit function here. Maybe we could just move over here while we're looking at it again. So marginal product with decreasing returns, our output is increasing, in this case our profit here, but at a slower rate as we add more labor here and more material here. And sort of, you can see the sort of the curves here. Starts out at a very high rate and then it sort of flattens out. Both cases here. This is for the material over here. This is the labor shown over here. And this was our maximum output based on the constraints we have. Okay, so that's the understanding here when we'll go back to it here. Okay, so let's go down and let's just look at the numbers here for our marginal product based on those differential equations that we come up here for marginal product of material and marginal product of labor. Now remember, those are the output here based on the last unit added here. So I've got a little table showing here, and I'm just saying I put in the same number here for material and labor. Just put that into our marginal product here for that we're showing here based on those differential equations that we have. So at 1 unit of material and 1 unit of labor, our marginal product here for material is $704 here. So we're adding $704 here to the output for that first unit of material. And if we look at a marginal product of labor, for the first unit of labor, we're adding $450 here. And remember, those really are functions of, and we could go back to it, but that's really the function of those exponents in our production equation here. So then we go down here, let's look at 10 units here. Marginal product drops, well, this is where we have 10, I added, just put into the equation here, I put 10 units of material here, and also 10 units of labor here into those equations. So for our margin product of material, we've gone from 704 down to 471. Margin product of labor from 450 to 300. And putting in, looking at 20 units of material and labor, we dropped from 471 down to 417 for material, and then marginal product of labor from 300 to 266. And if we went down to 60 units here, we go to drop to 344 and 219 respectively. And at 100 units, we're only adding 314 here to our output for material and 201 here to our output for labor here. So what we're looking at, marginal product of labor and material, we're looking at the output of the last unit added. And I'm just looking at the case here where I added the same number of units here for material and labor and put it into those differential equations that we looked at. Okay, so you can see they're decreasing. Now, they started out with that first unit at a pretty high amount, and then when you get up to that 100th unit, you're only, in this case, you're putting out less than half of what you started with the first unit, or the next units here. So you could do that for each of the units that we're looking at, and I just set material and labor equal to the equal amounts here when I put them into the equation. And then your output here, you can see, well, it's increasing here. For the first unit, 1,400. Next, the 10th unit, we got 9,356. And then up to that 100th unit, we're getting up to 62,535. So you can see it's increasing here. Okay, so let's just maybe take one last look here just to get a side view here of that marginal product for decreasing returns here. So just looking at it again for a marginal product here, it's increasing here. But again, let's look at it. Material here on this axis, it's increasing, or material quantities are increasing here, and then the labor quantities are increasing here. So just the idea is to look at this curve here, looking at material. So you start out with a real high marginal product for those first units. You can see it here. Actually, that first unit we're looking at, it was that 704 amount. Now, the curve here isn't really, it's representative of our differential equation here, but that dot here may not be, because that dot here, well, that dot here is relative to, for our material is relative to our labor here, and I use it for that first unit here. It really should have been shifted maybe over at 1 unit here, but nonetheless it's on the curve here. So you can see the marginal product start out high and it just kind of tapers off here as you increase the quantity of material, units of material going down. And so that's showing it here for material, that greenish curve here, and then that gold curve was for our labor here. Now let's just move over here again. Now again, marginal product is up here, going up here, and we're looking at it in terms of our labor here. And you can see how that curves down by looking at its profile here. You can see that the gold here is our labor. More first unit, we got a really high marginal product here, but as we add more and more units, we taper off and sort of flattens out here at a amount that you're looking at. We went from here 0 to 150 here for labor. All right, that's shown in gold here. You can see how it's going down. Decreasing marginal product for it. So that's the idea here. Just by looking at the equations, it probably doesn't tell us a lot, but when we look at these plots here, it really tells us a whole lot. When you can see by increasing those amounts of material and labor here, you're increasing your profit, but at a much lower rate than when you initially start out. Okay, so I guess this will pretty much summarize our discussion here just by looking at these 3D forms here for our marginal product here in what we call decreasing returns as we increase the quantity or the units of material and labor that we looked at in this case.